Welcome to the deep dive. Today, we're venturing into a really visually stunning world within computer graphics, Raymarching.
It's pretty amazing stuff.
We're going to explore how you can get this incredibly intricate art basically straight from mathematical formulas.
It's a fascinating approach, really. It shares the same kind of end goal as, ray tracing, making images by tracing light rays.
Right. Ray tracing, I think most people have heard of that.
Exactly. But Raymarching goes about it very differently. It relies on something called distance functions, or sometimes sign distance functions, SDS.
Okay, SDS distance functions. They sound, well, fundamental.
Oh, they absolutely are. They're key. Essentially, a distance function is like a rule. For any point you pick in 3D space, it tells you the shortest distance from that point to the surface of the nearest object.
Huh. So instead of defining an object by its, skin, its polygons,
Yeah, forget the triangles for a moment.
you're defining the whole space around it based on how far things are from a surface?
Precisely. That's the big shift in thinking. No polygons, no vertices in the traditional sense. You define the scene using this distance information everywhere.
That's really different.
And the real magic is how well this works for procedural stuff. Complex, organic shapes, things that would be a total nightmare to model with polygons.
Okay. That makes sense why it's good for things like... Well, the sources mention those amazing clouds in Xenoblade 2.
Exactly. Those kind of ethereal, almost endless clouds. Perfect example.
Yeah, they looked incredible.
Or the backgrounds in that anime, Sekai Surukado. Again, situations where traditional modeling would be super difficult, maybe even impractical.
Right, I remember seeing those visuals. It also mentioned something about efficiency and conciseness, especially for, Demoscene stuff.
Yeah, the Demoscene context is interesting. There, the actual size of the program is a huge constraint, like tiny kilobytes sometimes.
Wow.
So because Raymarching can describe really complex scenes with pretty compact math formulas, well, it's perfect for that. You get stunning visuals from very little code.
So it's efficient in terms of code size. What about, processing power?
Well, that's the trade-off. It can be quite demanding on the GPU, the graphics card. But hardware is always getting better, so it's becoming more and more practical for games and other things, too.
Okay. So we kind of get the what and why. Let's dig into the how. How do these distance functions actually, find a surface?
Right, the process itself. It starts kind of like ray tracing. You cast rays out from the camera through each pixel on your screen.
Standard procedure? Okay.
But then, for a given ray, at its current point in space, you evaluate the distance function for the whole scene.
And that tells you?
It gives you a number. Let's call it D.
Yeah.
And D is the shortest distance from that point to anything in the scene, like the absolute minimum distance to the nearest surface.
Okay. So you know how far you can travel from that point in any direction before you hit something. Guaranteed.
Exactly. So you take the ray and you move it forward along its path by exactly that distance, D.
You take a step. A safe step.
A safe step, precisely. Then you repeat. You evaluate the distance function again at the new point.
And you get a new D.
You get a new, probably smaller,
Yeah.
D. Keep doing this.
Yeah.
Evaluate D, step forward by D, evaluate step
Until
that distance D becomes really small.
Yeah.
Like practically zero.
And that means you've basically bumped right into a surface.
You got it. You've arrived.
Yeah.
It's not about calculating exact intersection point directly, like in ray tracing. It's more like feeling your way forward in safe steps.
Okay, iteratively getting closer. Is that the marching loop the sources mentioned?
That's exactly it. That whole cycle.
Yeah.
Check distance, step forward, check distance, step forward. That's the marching loop.
Gotcha. And what about sphere tracing? I saw that term too.
Yeah, sphere tracing is a great way to visualize it. That distance D, it basically tells you that you can draw a sphere around the tip of your ray with radius D, and nothing from the scene will be inside that sphere. It's empty space.
Oh, right. Like a little safety bubble.
Exactly. So each step, moving forward by distance D, is like taking the biggest possible leap you can while staying inside that guaranteed empty sphere.
I can picture that, stepping from one safety bubble to the next, getting closer each time.
That's the essence of it.
Yeah.
And that step-by-step movement is why we call it ray marching. You're marching the ray towards the surface.
That clicks. Really clear visualization. Now, The sources showed some amazing things with combining these functions, creating complex shapes out of simpler ones. How does that work?
This is where it gets really elegant. So imagine you have two different shapes defined by two distance functions, D1 for the first shape, D2 for the second.
Okay, two shapes, two functions.
If you want to combine them, like merge them into one single shape,
Yeah.
you just take the minimum of the two distances at every point. Mine, D1, D2.
It's the minimum. That's it.
That's it. The minimum distance effectively gives you the union of the two shapes. They just blend together.
Wow, that's simple.
It is. And if you want the intersection, the part where they overlap,
Let me guess. The maximum.
you got it. Max, D1, D2. That gives you only the parts that belong to both original shapes.
That's incredibly neat compared to, like, Boolean operations in normal 3D software.
It feels much more direct mathematically. And subtraction is cool too. You take one distance function, say D2, flip its sign, make it negative, and then take the maximum with D1. Max, D1 dash D2.
And that cuts the second shape out of the first.
Yep. Creates a cutout. It's surprisingly powerful, these simple min, max, and negation operations. You can build really complex things.
It really changes how you'd think about building a scene. Less about surfaces, more about space itself.
Exactly. Defining fields, really.
Okay, what about repeating things? The sources mentioned something about infinite patterns, maybe called an OOP leap.
Right, yeah. Sometimes you hear terms like that. It basically comes down to using math operations on the coordinates themselves, like the modulo operator.
A modulo, the
Yeah.
remainder after division.
Yeah. If you apply modulo to the x, y, or z coordinates before you calculate the distance function for your basic shape.
It makes the space kind of wrap around.
Exactly. It makes space repeat itself. So your single object definition suddenly appears tiled infinitely in every direction or along certain axes.
So define it once, and then one math trick gives you endless copies.
Pretty much. That's the power of procedural generation with this method. Combining these simple rules, union, intersection, subtraction, repetition, lets you build incredibly intricate structures from very basic starting points.
Like generative art, almost. Simple rules, complex results.
That's a great way to put it. It really feels like that sometimes.
Okay, so we can build these complex repeating scenes, but how do they interact with light? How do you know which way a surface is facing for shading?
Good question. You need the surface normal, right? The direction pointing straight out from the surface at the point you hit.
Yeah, for lighting calculations.
So once your marching stops, because D is tiny, you've found your collision point. To get the normal there, you calculate the gradient of the distance function.
The gradient. Okay, math term. Can you break that down?
Think of the distance function value as like the height of a landscape.
Oh.
The gradient at any point tells you the direction of the steepest uphill slope.
Okay. The direction of fastest change.
Exactly. And in the context of the distance function, that direction of fastest change points directly away from the surface. That's your normal vector.
So the distance function itself contains the information about the surface orientation, too.
It does. It's all encoded in there once you have that normal vector.
You can do standard lighting stuff. Shadows, reflections.
Yep. All the usual 3D graphics lighting techniques can be applied using that normal. It slots right into familiar rendering pipelines at that point.
That's really elegant how it all connects. And because this is often done in shaders, right? Those little programs on the graphics card.
Usually, yes. Written directly in shader languages like GLSL or HLSL.
It must give you a really, raw understanding of how rendering actually works.
Absolutely. Bypasses a lot of the higher level abstractions you might use otherwise. You're really working closer to the metal, dealing directly with the geometry representation in the ray process. It's fantastic for learning the fundamentals.
Yeah, I can see that. A great way to really get the rendering pipeline.
Definitely.
Okay, so let's just quickly recap the core idea then. Raymarching. Define your 3D world with distance functions.
Right. Math formulas describing distance to surfaces.
Then you shoot rays, and instead of finding intersections directly, you march along the ray.
Step by step, using the distance function value to know how far you can safely step each time.
Until you get really close to a surface.
And then you can figure out the surface normal from the distance function itself and do your lighting.
Allowing for really complex, procedurally generated scenes from surprisingly simple descriptions.
That's the heart of it. Concise description, potentially very complex output.
And we saw applications not just in games and demos, but art, visualization.
Oh yeah, the applications are really broad. That website we mentioned, Inigo Quiles' site, it's just packed with mind-blowing examples. Fractals made by folding coordinates.
Folding coordinates?
Yeah, using math to warp space before calculating the distance.
Yeah.
It creates these incredible recursive patterns. There's just so much ingenuity in the Raymarching community.
Hmm.
Diving into the code examples is, well, it's a rabbit hole, a fascinating one.
It really sounds like it, a field with a ton of depth and creativity.
For sure. Always something new being discovered.
Well, this has been a fantastic deep dive into the world of Raymarching. It's given me, and hopefully you listening, a much clearer picture.
Hope so. It's a topic worth exploring.
So as we wrap up, here's something to think about. A question for you, our listener. If you could actually design a world using these distance functions, defining everything purely with math, what kind of unique, maybe impossible scenery would you dream up?
Ooh, good question.
What would that look like? It's kind of a wild thought to ponder, isn't it?